So week 18 is simple harmonic motion. Okay, so let's get into it. So first of all, what is simple harmonic motion? I wrote SHM as an abbreviation because simple harmonic motion is kind of a long word, right? And then we're going to review springs. We did springs back in week 7, and we're going to review them because they're really important for today. We're going to look at a reference circle. It's what we call a reference circle, and then the sinusoidal nature of simple harmonic motion, the simple pendulum, and then the physical pendulum, 2 different types of pendulums. Okay? Go to the topic. So what is simple harmonic motion? So the definition is up on the screen. Any motion in which the force F on an object is proportional to the negative of the distance the object is from an equilibrium point. So what this means is that if I set a location as the equilibrium point, and we're going to have a positive and a negative direction, if this object is a distance x away, then the force is proportional to x, which means that F is going to be proportional to x. F is going to have to equal to a constant k. Okay, it could be any constant multiplied by x. Okay, and has to be negative of that, which means the force will be in the opposite direction of the object's position. So if the position is positive, as in this case, the force must be directed negative. So as you can see here, the force is always going to be directed towards the equilibrium point. Say if the object were here, then the force would be directed positive direction. So the force will always direct the object towards the equilibrium point, and the equilibrium point is where the net force is 0. Okay, so that's simple harmonic motion. The object will oscillate back and forth because once the object passes the equilibrium point, it will start decelerating. It will stop and it will turn back and it will go all the way. It'll keep oscillating between these 2 points. Okay, so this is called simple harmonic motion. And the equilibrium point is in the middle of that, where the net force is 0. Okay, so if the object is at equilibrium point, then there's 0 force on it. So any kind of motion where this is true is simple harmonic motion. All right. So that's why we need to review springs, because as you know, in springs, we have a formula where the force of a spring is equal to kx, and the force is always directed in the negative direction of displacement. For example, if I were to have a string here at relaxed equilibrium point, if I were to compress the spring, the distance x, let's say this is positive and negative, distance x is positive, so the force must be negative, and the force would go down towards the equilibrium point. So springs are simple harmonic motion. Okay, so that's the first part. That's why we need to review springs, because they're really important for simple harmonic motion. We're going to be looking mostly at springs for this topic. All right, so F equals negative kx. So one other thing you guys should remember about springs is that the energy of a spring, the elastic potential energy, is 1/2 kx squared. All right, and then what else is there? Well, the equilibrium point. The definition of the equilibrium point, once again, is F net equals 0 for EQ point. That's the definition of it. Okay, so this means that for a horizontal spring, an object like that, for F net to equal to 0 in the horizontal direction, then that means the spring must be unstretched, because otherwise there would be a non-zero net force. Okay, so for a horizontal spring, the equilibrium point is at the unstretched position. For a vertical spring, it's different. All right, because for a vertical spring, if the spring were unstretched here, then the mass here, there's a mg going downwards, right? Gravitational force. So at this point where the string is unstretched, then the net force on the point mass is not 0. So this means that this cannot be the equilibrium point. The equilibrium point must actually be lower, at distance x lower, so that the returning upwards spring force will balance out mg. So in this case, kx equals mg, because it must balance out, so x is mg over k. So this is the distance from unstretched position for the new equilibrium point. The equilibrium point has a new value because the equilibrium point is defined as where the net force is 0. So the equilibrium point must be at a lower position so that the spring force can go upwards. Okay, so now let's look at how springs oscillate. Okay, so oscillating means that we're going back and forth between a point, and that's what simple harmonic objects do. For example, if I were to take this object right here, let me delete some of this. Let's say a point mass here, this is the equilibrium position. If I were to compress it so that it was up here, then there would be a greater spring force and the gravitational force pushing it down. So it's going to go boing, and then at this point, the spring force is going to return it back up. It's going to bounce back here, on and on and on and on and on. It's going to bounce up and down, up and down, up and down. Okay? So there are parts of this motion that we need to define. The amplitude, which I will label with a capital A, the amplitude. The amplitude of motion is the distance from the equilibrium point to the maximum compression or maximum stretch. So the amplitude is the same for compression and stretching. All right, so the amplitude is the maximum distance away from equilibrium point that the point mass will either stretch or compress. All right, so that's the amplitude. Okay, so from this, we can figure out what's the maximum speed of the object. What's the maximum speed that this object obtains? Because at the amplitudes, the net speed is 0. It just kind of stops there. And then it accelerates downwards until it stops again and bounces back up, right? So there must be a point where the velocity is highest. So then we can just use conservation of energy, all right? Because 1/2 Ka squared, in the instance where the point mass is at the amplitude, then all the energy in the system is stored inside the spring. So this is the total energy. And the total energy will also equal to 1/2 K V max, not K, 1/2 mv max squared. Because at this point, then there's just going to be kinetic energy, right? So the maximum speed obtained is when there's no spring energy. So we can set these two values equal to each other, and we'll get V max equals the amplitude times the square root of K over M. And this is the first of many simple harmonic formulas that we need to memorize. So write this down in a notebook or something. But this formula is actually just derived from the conservation of energy. So this one you shouldn't really have that much trouble memorizing. All right, so this is the formula for the maximum speed the object will obtain just by using conservation of energy. Okay, so that's a review of springs. Are there any questions? All right, so before we go on, one other thing I need to mention is that T, the period. So the period of oscillations is the amount of time it takes for one cycle to complete, which basically means, for the bob to start either from the bottom, go to the top and come back, that's one period, or from the top to the bottom and come back. All right, so both of these are equal to the period. The period is time takes for one cycle. Okay, and then similarly, the frequency, which is equal to 1/t, is equal to the number of cycles per second. All right, so these are basically more review. All right, so all of these things are review. And so now let's go on to actual simple harmonic motion, things that are new. So we have what we call the reference circle. So let me draw out the reference circle here. The reference circle is really important for any kind of simple harmonic motion. For any kind of simple harmonic motion, you're going to have to relate the situation to a reference circle to solve your problems, okay? So imagine we have a vertical circle here. The circle is vertical. It's like it's standing upright. And then we have a bead that's going around the circle at a constant speed or constant angular velocity, W. Okay? It's going around at a constant velocity. And let's say we have a very large and bright light. okay, like a fluorescent light, and shining upon the bead. And let's pretend that the hoop itself is very thin, so we can't see any shadow, but we can see the shadow of the bead. So there's going to be a shadow right here. And if you imagine this bead going around the circle, the projection of its shadow is going to be going through simple harmonic motion, because when the bead is right here, then the shadow is here. When the bead is right here, the shadow reaches here. But when the bead starts going backwards, when the bead goes here, then the shadow returns here. So it's like going like this. And then it will go all the way over here and bounce all the way back, because it's going around in a circle. Okay, so this is the reference circle. We can pretend that if we have an object going in simple harmonic motion, then the object is the shadow of a bead going around a circle with a constant velocity, with a light shining down on it, such that the velocity or the position of the object in simple harmonic motion is the projection of the shadow of the bead onto the floor. Okay, does everyone understand this reference circle?
What do we use it for?
Yeah, I'll get right into that. So as you can see in the reference circle, the equilibrium point is right here. Because at this point, this is directly in between the amplitudes. The amplitudes are going to be like the radii of the circle, right? Because these are the maximum distances the shadow can be away from the center. Okay, so first of all, the amplitude is the radius of the circle. Okay, now the W, because we have a constant angular velocity, we can represent constant instantaneous velocity here as well. So any point on the bead will have a constant velocity. And the funny thing is that this velocity equals the maximum velocity of the shadow. Well, why? Because since the position of the object is a projection, then the velocity is also a projection, which means that the horizontal component of velocity at any point, v horizontal, is the velocity of the shadow. All right, so the horizontal component of velocity of the bead in the circle at any point is equal to the velocity of the shadow. Because here, the velocity of the bead is directed straight down, which means that there's no horizontal component, and that's why the shadow seems to stop right there. And then the maximum speed obtained is right here, because there, all the velocity is horizontal. And at that point, that's the equilibrium point, meaning that's where the maximum velocity is, and that velocity will equal to V max. So V of bead is equal to V max of shadow. Okay? So we can use this reference circle to find the equation for the period of simple harmonic motion. Right? I told you that period is the amount of time it takes for one cycle, but I never told you what the formula for that was. Right? So now that we have a reference circle, we can represent the period of one cycle as the same thing as the time it takes for the bead to go around the circle, right? Because that's the same thing, because the shadow is just a projection of the bead. So the period is equal to the amount of time for the bead to go around the circle. Well, Vt equals d, so t equals d over v. So what's the distance this bead needs to travel? Well, it's going along the circumference of the circle, which means that d is 2 pi times a, because a, the amplitude, is the radius of the circle. Now the velocity is the velocity of the bead going around the circle, right? And the funny thing is, that's equal to V max, remember. So we can replace this with V max inside. So now we have this formula for the period of the oscillations. But this is not yet in the simplest terms, because we know that V max equals A times the square root of K over M, right? We did this on the last slide. So we can substitute V max in right here. So if we do that, what do we get? If we do that, we're going to get 2 pi square root M over K after some simplifying. And this is the period. This is the second formula you guys should remember here. All right? So the period is equal to 2 pi times the square root of m over k. And the cool thing here is that you can see that the amplitude is not considered in the period. So the amount of time it takes for one cycle does not depend on how far the spring was stretched. All right? This makes sense because if you were to stretch the spring farther away, then it would shoot back much faster. There's a longer distance, but it's also going at a higher velocity. Okay, so that's why the period is constant for a constant mass, a constant spring constant. Okay, does not depend on the amplitude. So likewise, since f frequency is 1 over t, you can just take the reciprocal of this. F equals 1 over 2 pi square root k over m. Okay, so that's basically it. All you really need to remember is this formula right here. You don't even really need to memorize the frequency formula because that's just the reciprocal of the period formula. All right, so this formula is really, really important. Okay, are there any questions? Cool. 3 problems here. Or you guys can skip the second one because it's basically the same thing. So take 5 minutes to do these. Chat me your answer. For the second one, function of distance x and v max and a. So the speed of the mass should be a function of v max, a, and its distance x. Okay, all 3 of those. One more minute. All right. So for the first one, we're just going to use t equals 2 pi, the square root of m over k. You just need to plug in values. So m is 3, k is 200. So you should get around 0.77 seconds. And frequency is just the reciprocal period. So you can just do 1 over whatever this is. So that's like 1.29, 1.3. Should be 1.3. Remember, the units we use for frequency are hertz. Okay. Now for the second one, we're going to have to use conservation of energy to find the speed of the mass as a function of the distance the object is from equilibrium. So all we need to do is use conservation of energy here. So let's just first draw a diagram. So here, this is the equilibrium point. And let's say the object is here, and the amplitude is right here. Okay? So the total energy in the system can be represented as the situation where all the energy is stored as potential energy. So the total energy is equal to 1/2 Ka squared, because at that point, all the energy is comprised of the potential energy in the spring. And similarly, the total energy can be represented here as 1/2 Kx squared, that's the elastic potential energy, added to 1/2 mv squared. Okay? So if we just set these two values equal to each other, here, 1/2 k squared. Now if we do a little bit of simplifying, we're going to get v squared, or v itself, equals k times a squared minus x squared over m, squared of all of that. But the problem wants us to get rid of k and m and replace it with v max. And remember how v max is just a times the square root of k over m? We do have square root k over m here, so we can just replace that with v max. So if we take this out and replace it with v max, then we get v equals v max, the square root of a squared minus x squared, all over the amplitude. Okay? So then we can put this outside, we can put this a inside the parentheses, inside the square root, and making it a squared. And we can do a little bit of simplifying inside. V equals v max, the square root of 1 minus x squared over a squared. And this actually is the other critical formula, another critical formula you guys should remember. This is velocity as a function of the distance away from equilibrium and v max. All right, so this is a critical formula. And we can derive the exact same formula by using the reference circle. That's how useful the reference circle is. So let's draw the same situation. This is EQ, this is X, and let's say A is here. If we draw the reference circle, let me draw a better reference circle actually. So as you can see here, I made the radius equal to A. The radius of the circle is equal to A. So now what? Well, we know that at any point on the reference circle, the velocity of the object is the horizontal component of the velocity of the bead. So if the velocity of the bead is going like this at an angle, then we want to find this. This is equal to v. These are the exact same thing. So that's what we want to find. We want to find this horizontal component. Let's say this is theta. So now we got to find another situation where we can use theta. if we draw a line right here, and we draw a perpendicular down, doing some geometry, you can see that this is theta as well. All right, so the v we want to find, remember, the velocity of the bead is going to be v max. So v is going to equal to v max times the cosine of theta. Now, what is the cosine of theta? Well, we have a right triangle here. The radius is a, so the hypotenuse of the triangle is a. And right here, we have x, because that's literally what x is. And this part is going to be the square root of a squared minus x squared by the Pythagorean theorem. So the cosine of theta is going to be the adjacent over the hypotenuse. So cosine theta equals the adjacent over the hypotenuse. Oh, doing a little bit of simplifying, we can put the a squared inside the square root, and we get cosine theta equals square root of 1 minus x squared over a squared. Oh, look here, if we just plug this guy in, we get v equals v max square root of 1 minus x squared over a squared. We got the exact same answer. So this is how useful this reference circle is. So whenever you are stuck on a simple harmonic motion problem, try the reference circle. It might help. All right. Are there any questions? Cool. I've got the sinusoidal nature of simple harmonic motion. So the thing is, for simple harmonic motion, we can represent the position x as a function of time. So if we visualize, let's say we have a spring here with a block attached to it, and it's oscillating up and down. And let's say there's like a blob of paint on the block. And if we have a piece of paper and we pull the paper to the left, then the block will trace a path kind of looking like this, because it bounces up and down, and it goes slowest here, and it speeds up, goes slow, speeds up again. And as you can see here, this graph looks so much like the sine x graph, cosine x graph. And that's exactly right. We can represent any kind of simple harmonic motion with x as a function of t, where x is, we use the sine or cosine trigonometric functions. Okay, so recall that the general form of a function is y equals a times the sine 2 pi over period times time. Okay, this you learned in trigonometry. All right, so this is the general form of a sine or cosine function, where a is the amplitude, which is basically how high it is, and t is the period of the function. All right, so if we want x as a function of time, then x here is the dependent variable, t is the independent variable. So x is going to replace y, t is going to replace, oh, right here, this should be x. So t is going to replace x. So x will equal to a times the sine 2 pi over t times time. And don't confuse the capital T with the lowercase t here. The capital T is the period, right? With the period given by 2 pi, the square root of k over x. No, m over k. Okay? That's the value. That's a constant, okay? And t here, the lowercase t, is time. T equals 1 second. T equals 2. This is the variable that's changing, and x is depending on lowercase t. And a here is just the amplitude, because obviously, if we take 0 as the equilibrium point, then the amplitude is just literally just the amplitude of the spring motion. All right, so this is the way you can represent the position of the spring as a function of time. All right, so if I were to graph this, we're going to have position and time. It's going to look like this. Does everyone get this? All right, but the problem is if we use the sine function, note how the sine function is going to start at 0, 0. Right, because the sine function always starts there, because if t is 0, then the sine of t is 0, then x is 0 as well. Okay, but what if the object doesn't start at equilibrium point? If we did the sine function, then it means it has to start at the equilibrium point, because it's at 0, 0. If it starts at maybe the amplitude, then what do we use? Well, we can just use the cosine function. We can just replace the sine in there with cosine. All right, so if we use this function, then the graph would start at the amplitude and go like this. All right, so it depends which you would use depending on the situation. So if it starts at equilibrium, you're going to use a sine function. If it starts at the amplitude, you're going to use a cosine function. Okay, are there any questions? All right. 2 problems. I'll give you guys 5 minutes. And chat me your answer when you get it. One more minute. Okay. So we want to write the equation that represents x of the box as a function of time. So first of all, we need to figure out, are we going to use cosine or are we going to use sine? It starts at the equilibrium because it says at time 0, it starts, is moving past equilibrium, which means it's at equilibrium. So we're going to use the sine function here. All right, so it's going to have x is equal to a sine 2 pi over period times time. We're going to have to find a and find period. Then we just plug these values in to get our function. So what is a? Well, we know that v max is equal to a square root k over m. We have v max here because when the object is going past equilibrium point, it's at the maximum velocity. We already have k, we already have m, so a, we can just solve for a now, right? So a is going to equal to v max squared times m over k. So that's just going to be 5 squared times 5 over 400. A should be around 0.3. Okay. So now we have, wait, actually that's not right. A squared is equal to that. Sorry. So all we need to do is take the square root of what we just got, 0.56. Okay. So now we already have A. We just need to solve for period. So what is the period? Well, period is 2 pi m over k. We already have m, we already have k. So what is that? 5 over 400, take the square root, is 2 times pi, 0.7. So all we do is plug a in here. A is going to be 0.56. 2 pi over t, so we got to do 2 pi over 0.7, 8.9. That's it. We have our function. All right. Next one is very similar. We're just going to do it the opposite direction. So we want to find the amplitude. The amplitude is this value. It's that value right there. So A is 5. The period. Well, 2 pi over t is 3. So t is 2 pi over 3. So 2 over 3 is pi. It's going to be 2.1. B, 2.1. The frequency. Well, that's just the reciprocal of 2.1. 0.48. Maximum velocity. Well, we know that V max is equal to A times the square root of K over M. We have K, we have M. So the square root of 125 multiplied by A, which is 5, 56. Oh, we forgot to take the square root. Actually, never mind. I don't think this is very realistic then. D equals 56. Because normally, we're not going to stretch it 5 meters, right? So obviously, it's not going to be realistic. The total energy of the system, well, the total energy is given by either 1/2 Ka squared or 1/2 mv max squared. You can choose whatever one you know. Okay, you already know V max, you already know A, so you're going to get the same value. So 125 times 5 times 5 times 0.5. You're going to get 6,250 joules. All right, any questions? So normally it's not going to be that much, that high of a velocity, because you can't really stretch a spring that far, 5 meters. It's just unrealistic. All right, now I've got the simple pendulum. Simple pendulum is a mass on one end of a very long and light string. It doesn't have to be very long, but it's relatively long and relatively light compared to the mass. So we can assume that all the mass of the system is centralized at that point, and it's pivoted at the top. So it kind of swings back and forth, and it comes back. Obviously, it's oscillating, right? So we can assume that it's simple harmonic. But how do we prove it? Simple harmonic means that we have to have F proportional to negative displacement. Okay, so in this case, it's going to be X right here, and EQ is right in the middle. So how do we find this? Well, what is the force accelerating the mass this way? Because that's what we really want to find. Well, we've got tension force, but tension force is perpendicular to that. So it doesn't really do anything. So we can completely ignore tension force. The only force we got is mg. All right. If this is theta, if we draw the dotted line here, then this is theta as well. So we can see how the force here is mg sine theta. So F is equal to mg sine theta. All right, but we still don't have position in here. We don't have x. We got to get x. So how do we get x in there? Well, now we're going to use a simple trick, okay? The trick is that we can use the approximation that sine of theta equals to theta for small angles. And theta here is going to be in radians, okay? So for small angles, we can assume, we can represent sine of theta as theta itself, all right? It's going to have some kind of error, but it's going to be small for a small angle. Once the angle gets big, then the error is going to get bigger. So we can't use this for a bigger angle. So if we replace sine theta with just theta, then let's see what we get. If we replace sine theta with theta, then we get mg theta. And remember how theta times r equals distance? If we relate it to this case, if the length of the string is L, then theta L equals x. So theta equals x over L. So let's replace this with x over L, mg. Oh, look, there we have it, proportional to x. All right, and this only worked because we assumed that sine theta equal to theta. So for this, a simple pendulum will only be simple harmonic if the angle is small, because otherwise this assumption would not be true, and this would also not be true. All right, so simple pendulum will only be simple harmonic if theta is small, or only for small angles. All right, so here we can assume that mg over L, that could be like the k value, right? So we can use this to find the period of the swing of the pendulum. We can use this to find the period, because we know that period is 2 pi the square root of m over k. K in this case is mg over L. So T is equal to 2 pi square root of L over G. And this is the formula for the period of a simple pendulum. As you can see here, it doesn't matter what the displacement is once again. Only matters the length of the string and the gravitational force going downwards. Any questions? Cool. 2 problems. Running a little low on time, so how about just take a shot at the first one. The second one is very similar. One more minute. Okay, so for this one, we're just going to use period equals 2 pi square root L over G. It's going to be around 3.48 seconds. All right, and if you haven't written this formula down, write it down. All right, this is going to be one of the important formulas for simple harmonic motion. Okay, are there any questions? Okay, so now I've got the physical pendulum. The simple pendulum was where all the mass was concentrated at the end of the string. The physical pendulum can be any kind of object pivoted at one end, and it's swinging back and forth. For example, we could have a rod, a uniform rod, and it could be swinging back and forth, back and forth. We could have a hammer. So a physical pendulum is any solid object that swings back and forth, back and forth. All right? And the proof for the formula of a physical pendulum is very, very similar to the proof for a simple pendulum. So maybe I'll put that in the homework. But for now, just memorize T equals the square root of I over mg d. So I is the inertia of the solid object. Okay, moment of inertia of the object. M is the mass, G is gravity, and D is the distance from center of mass to pivot. So the center of mass of the hammer is right here, then D is going to be this value. Okay, so this is another one of those important formulas. T equals 2 pi square root of I over mgd. Okay, so once you guys have written this down, let's go on to a few problems. And the proof for this formula is very similar, and maybe I'll give you guys that as a homework challenge later on. Okay, so once everyone has that down, let's go into some problems. So before we go on, the inertia is not just the inertia around the center of mass. The inertia is specifically has to be the inertia around the pivot point. For example, if we have a uniform rod, then inertia would be 1/3 ml squared, because that's the inertia around a point, okay? Around one of the ends. If it was around the center of mass, then it would be 1/12. But we have to take the inertia as around the pivot. Okay, so that's one extra detail. All right, two problems. One of them is a normal problem. The other one is from the 2020 FMA B. This is from this year. Okay. So this one was actually one of the easier ones. It's a direct application of the formula previously mentioned. I'll give you guys 2 more minutes. The one from the FMA is a little bit challenging. You need some of your previous knowledge from rotational motion classes. All right. So for the first one, I'm just going to use t equals 2 pi, the square root of I over mgd. So what is I? Well, it's a uniform rod on the ceiling. Okay. Oh, my bad. So I think the answer I gave you guys might have been wrong. So I made a mistake. I thought it was 1/12, but it's actually 1/3 ml squared. Apologies for that. So 1/3 ml squared actually over mg times, well, what's the distance from the center of mass to the pivot? It's just 1/2 the length of the rod, right? Okay. So erasing this, mg times L. Oops, wrong pen. Well, now let's do a bit of canceling. M will cancel. L kind of cancels. We're going to have, oh, I forgot 1/2. So we're going to have 2 pi, the square root of 2/3 L over G. L is 3, G is 9.8, 3 over 9.8 times 2/3. Take the square root, there's 2 times pi, 2.8. All right. Next one. We're going to use the same formula. We want to find the period. T equals 2 pi square root I over mg d. We know what m is, we know what g is, we know what d is, because that's just r. But the inertia, that's the hard part, because we need to find the inertia around the pivot point. Okay? It's not going to be through the center of mass like this. It's going to be like this. Like, for example, if I were to draw it like this, it's going to have to go like around this axis. So we want to find the inertia of a cylinder around that axis. Well, first of all, you got to find the inertia through the center of mass around an axis parallel to the plane. And for this, we're going to use Iz equals Ix plus Iy. Remember that from the inertia equations. So Iz is the inertia perpendicular to the plane of the cylinder. Ix and Iy are the inertias perpendicular to each other and perpendicular to z, but they're parallel to the face of the cylinder, which means that Ix and Iy can be like this, and Iz is going straight through the cylinder. Iz, as we know, is 1/2 mr squared, so 1/2 mr squared. And by symmetry, Ix and Iy are the exact same thing, equals 2Ix. So Ix equals 1/4 mr squared. All right, so the inertia around this point, this pivot right here, 1/4 mr squared. But now we got to move it to here. So now we're going to use the other formula. It's called the parallel axis theorem. I didn't tell you guys the name of it back during that class, but it's called that. where I nu is equal to I0, which is basically the inertia through the center of mass, plus the mass times the distance between these two axes. The distance is r, so we're going to have I nu equals, well, I0 is the value we found for Ix, plus m times r squared, because d is r. And I nu, finally, it will equal to 5/4 mr squared. We got it. So now this is the inertia. Just plug it into the equation now. So t equals 2 pi 5/4 mr squared over mg times r, because r is d. Cancel a little bit. The 4 will cancel with the 2 because the 4 is inside the square root. Pi square root 5r over g. And that's the answer. Okay. So if you remember from the equations from the rotational motion classes, and with this formula, that's all you really need for this problem. Any questions? Cool. So here are some general simple harmonic motion formulas. Take a photo, whatever you want, and keep it as reference for later on. And this formula, I did not mention it specifically in class. The maximum acceleration is a times k over m. This is just derived from F equals k times a, because that's where the maximum force is obtained. And ma is going to equal to k times a. A is just going to equal to a ka over m. Okay, so that's where that formula came from. Just a direct application of that formula. Okay? So that's it for mechanics. All right. If you've learned through this class, you should be good for the first semester of AP Physics 1 and for the F equals MA. All right. But of course, this class is like basically the bones, the structure, and you just got to do more practice now to get ready for the F equals MA. All right. So if you're not taking E&M with me later on, then it was a good time. I learned a lot. I hope you guys learned a lot too. But if you are learning E&M, then I will see you in 2 weeks. All right. Bye, guys.
Bye.
Thank you. Bye.
Bye.